Okay, question 3 is the one I like the best. List and define the 4 evolutionary forces that produce change over time. Well, the first one is the Holy Grail, natural selection. Basically, this is the process by which slow accumulated change, well, no, that's evolution. Natural selection is the process by which things that are beneficial to the organism stay and things that are damaging to the organism or deleterious are weeded out. The way by which it's weeded out is natural. It's not basically if you're a good replicator, if your mutation leads you to replicate better, then you out replicate the opposing mutation or lack of mutation. Say you have two populations. One has a beneficial mutation, sorry. The other one does not. Um, that beneficial mutation might not even deal with replication on its own. Um, it might make it a better eater, a more efficient predator. Um, the other one doesn't have this mutation. Uh, Population A finds food easier, then has more time to spend replicating, finding a mate. If it's a species that has sex, it has more time to, have sex. If it's a species that produces asexually, the more food it has, the easier it is to, the more energy it has, and the more often it can split into multiple things, asexual reproduction. The other population, though there may be nothing wrong with it, fundamentally, it simply can't compete. Nature has selected for Group A. Likewise, would be, well, we'll get to that in a second. The second thing is genetic drift. Now, genetic drift is basically um, basically measures the allele frequencies in a population. Um, it's considered a neutral force, so it's considered one of the 4 forces of evolution, and it could certainly give rise to mutations that wouldn't have been there for natural selection to act upon had genetic drift been there. You get what I'm saying? Had it occurred from genetic drift. Um, Allele frequency is basically something like a random sampling or how much. Alright, the word we use for gene actually doesn't mean anything. Gene talks about a collection of alleles. Now, to say gene is like saying a bundle of sticks. Um, Say the bundle is gene and sticks are the alleles. Would you say one stick is a bundle of sticks? No, of course not. 2 sticks? Nah, that's a couple of sticks. 3 sticks? That's a few. Let's say 4 to 5 sticks is a bundle of sticks. Well, what if you have more than that? What if you have an entire room full of sticks? Is it likely that you're going to be able to transport them without losing some of them? If not, you don't call that a gene because it's not likely to replicate to the next generation without getting ripped down the middle. That is allele frequency, the frequency of a stable allele in each generation. Um, that's what you're measuring, the frequency of specific alleles in a gene. Um, the third mechanism is mutation. Without mutation, you simply have nothing for natural selection to select for. um, Mutation is basically change, a random change that can either be beneficial, neutral, or deleterious, depending on what you want to emphasize. Deleterious mutations are bad mutations. In fact, while the nomenclature, I don't know how to say that word, but while the root word isn't delete, I don't think it actually is. Um, that's a good way to explain it. Deleterious mutations, since they lower their host chance of passing on that gene, essentially delete themselves. They're not going to be passed on to the next thing. I mean, they can, but for the most part, they don't. Neutral mutations are exactly what they sound like, mutations which are neutral. Now, in a future date, they might either be beneficial or deleterious because of how genes interact with each other, but at the moment, they are neutral. They can't be selected for or against. They are outside of that realm. Beneficial sorry, I'm tired. Beneficial mutations, of course, are again exactly what they sound like. Um, these will be selected for only if they improve the host chance to pass on that gene. Let me explain. Let's say you have a population that has a gene mutation that makes them live to 130, but it's in a species that can only mate once and it's in its 20s. Well, how does this gene help it mate? It can't mate after its 20s. Um, Furthermore, this gene has to be expensive. There has to be some cost that this gene is taking up for a gene to be this amazing. Um, we have a gene called the FOXO gene that keeps our bodies running. Um, let's say this overloads the FOXO gene. Well, if it doesn't do anything to improve the organism's chances of replicating itself, then it's not going to be selected for. Um, so yeah, even beneficial mutations might not be selected for. Um, all right. The last one is gene flow. Um, this actually explains diversity. Um, when a species is isolated, that changes its allele frequency. Um, it then has a completely different set of selection forces on it from its host species or whatever the original population was. Um, it gets different alleles, basically different genes to adapt to that environment. Um, I believe immigration is what it's called when these two species come back together. But even if they don't, there's going to be some transfer between individuals. If this occurs, that's gene flow. They're putting very unique alleles into each other's population. Those might be selected for powerfully. They might give a massive beneficial effect, a beneficial extended phenotype. Phenotype is effects of a gene outside its own body, on the environment, maybe even on other people's genes. Um, I lost my train of thought, but yeah, these might be selected for. What will eventually happen, though, is equilibrium. Uh, Basically, evolution outsmarts itself, I should say. Well, that implies thought, but the pressures equalize. They either use up too many of the environment's resources, various equalizing factors. But until it reaches equilibrium, immigration, that is, gene flow back into this system, could give a small group a massive benefit advantage.